things here. So power stuff can be a little bit heady. People are kind of generally getting an idea for some of these power calculations, what's going on with stuff. Okay. Last thing we're going to go through and talk about here is something known within sort of the math end of things as a non-centrality parameter. Now, our test statistic for our t-statistic is distributed around 0 so long as the null hypothesis is true, okay? If the null is true, right, and we were to go through and sample and try to calculate t-scores for a test where the null hypothesis is true, we get the sort of the nice t-distribution that we go through and table and use for all of our stuff, okay? The problem is if the null hypothesis is false and the mean of our population is not equal to the mean specified in the null model, then my t-statistic is no longer centered around 0 because we're subtracting the wrong population, okay? Basically, if I go through and I use my t formula, if I subtract something that's other than 0, right, what it ends up is I've got a t-statistic that's not going to be centered on 0, it's going to be shifted one way or the other, okay? And so here what we would say is my t-distribution, my non-central t-distribution is now centered around this point sigma, okay? And so this shift from 0, where the null hypothesis is true, off to a different value, right? On my t-distribution, we identify this as the degree of non-centrality, where sigma here is my non-centrality parameter, okay? You'll see this as sigma, you'll see NCP, things along these lines, okay? And so what we end up getting with this is my estimate of power starts to become related to how likely I am to find this value of the non-central distribution that's greater than my critical value under t. And so this is where that overlapping distribution thing sounds like. So here is my null distribution for t, right? Here's my non-central t, right? Because I've got a shift, right? And this shift from here to here, this is that sigma. How far off did it go through and shift, okay? And again, when I'm thinking about this in terms of overlapping distribution, it's how likely am I to find a t value in this non-central t distribution that exceeds whatever value is that would be specified under the null as evidence for an effect. Okay. So this is where that overlapping distribution piece starts to come into play. People have questions, are kind of seeing where this is coming from? Okay. So if I'm going through and I'm calculating for my power for a single sample t, okay, power is going to be, and I went through and I set this up in your handouts. You got a power table. Go through and pull that up if you would. I forgot to grab mine, but calculating power, we go through and sort of historically we've done this from tables based on specific values of my non-centrality parameter and my alpha level here. Okay, so if I go through and I calculate my effect size as my observed mean over my standard deviation, right, and my calculate sigma as my effect size divided by or multiplied by the square root of n, this will give me the stuff that I need to calculate to run a power calculation for a single sample t-test. So let's say we have this an example, a simple example. So the question is, do people seeking treatment for psychological difficulties have higher IQs, right? So this goes into this stereotype like, oh, this person's too smart. They get in their own head. So people who are more intelligent are more likely to have mental health problems. Okay, so we go through and we take a look, and let's say we've got a group of 25 individuals. We go through and we give them achievement tests. They have a score of 105. We have a mean, though, an expected mean of 100 with a standard deviation of 15 here. Okay. People see what we're doing, how we're setting up this test. So basically we've got a number of individuals who are maybe seeking treatment for psychological difficulties. And what we're doing is we're measuring their IQ and testing it against instead of our reference value. So this is just a single sample t-test. So I go through and I calculate my D statistic. So it's 105 minus 100 over 15. What's my D? What is it? 0.33. D 0.33. And I take 0.33, multiply it by 0.25, or square root of 25. What is it? 1.65. Okay. So I've got my test, my effect size, my non-centrality parameter. Okay. And so what I would do is I would go through and so I have I would go through with my power table. I would go through and scroll down to find something that's close to 1.65. It kind of falls between two values here, right? For a two-tailed test for 0.05, I'm falling somewhere between 0.36 and 0.40. Okay. People see that on their power table, where I'm getting that? Okay. So basically what this is saying is my power is going to be about 0.38. So as we were saying, assuming the null hypothesis is false, right? My effect is expected to reach statistical significance about 38% of the time, given a sample of 25 and a population effect of 0.33. People see how we went through and calculated that. So this is just, we're using that table to go through and extrapolate some values here. So again, when we think about this non-centrality parameter, that non-centrality parameter is just like a different version of an effect size, right? If my non-centrality parameter is bigger, it's going to imply a bigger effect size. If my non-centrality parameter is smaller, it's going to imply a smaller effect size. Because what we're looking at here is it's really giving me the difference between my null value and my actual population value, which is just my effect size, right? So we're just going through, and for the purposes of power calculation, taking this effect size and turning it into a slightly different metric. But that's essentially, so you can think about this non-centrality parameter as a measure, it's not a super interpretable measure of effect. So here I can say, if I just look at D, I'm saying that there's 0.3 of a standard deviation increase, right, above the null value. My non-centrality parameter, 1.65, that doesn't have a real literal interpretation, but it's essentially a measure of effect size. Okay. So what I could also do, and so this is fine, this is telling me the power that I've achieved, right? But more often what I might be interested in doing, or what I will be interested in doing, is wanting to know what's the sample needed to achieve a power of 0.80, right? Because that's what we're actually looking for, because that's acceptable power, right? Well, we can go through, this is easy enough to go through and sort of use my, use the formula here and just do some algebra on it and solve for n, right? And if we do that, we get n is equal to my non-centrality parameter over my effect size squared. Okay? And so here, I've got 2.8 over 0.33 squared. Where did I get 2.8? Yeah.
It's where 0.05 is.
Yep, exactly. From the power table, if I go down through, if I find a value of 2.80, that's the value that's going to correspond to power equals 0.8, right? So if I do that, if I take 2.8 divided by 0.33 and square that, someone run that and tell me what value I get.
71.99.
What is it, 71.99? So we'll call it 72 because I can't have 0.99 units of a person, right? So basically what this is saying, if this is truly the effect in the population, if I'm looking at an effect of 0.33, with a one sample t-test, I would need to have a sample of 72 to adequately power my, to give me an 80% likelihood of identifying this effect. People see how we've gone through and sort of just basically use some math to flip that around on its head. This is sort of our power that we've achieved. It's like achieved power. This is what we would project if our sample, or if our effect size is spot on. If we think that this is a credible effect size and I want to go through and develop a study where I have a good chance of identifying my effect, I need to have I should probably have about 75 to 72 people in that. Okay. So people follow how we went through and use those power. And again, so it's pretty simple for these sort of basic tests to go through and do. Any questions? All right. We'll also go through and calculate this for my independent sample t-test, okay? If I'm looking to detect power, detect differences in sample means, my effect size here is going to be the difference between my two means over the standard deviation estimate, and my non-centrality parameter is going to be equal to my effect size times the square root of n over 2, where n is equal to the number of cases in either sample, not my whole sample, right? It's just one of the two groups. But here, I'm assuming I have equal cell sizes. So let's see, in this example, we just want to know the difference in symptom means for treatment 1 and treatment 2. So we're testing 2 different treatments, right? And I know that the difference in my symptom scores is 5. I got standard deviation of 10 for both samples, because we're saying that we have equal samples and equal variances and things along those lines. I've got 25 in one cell, or one group, 25 in the other, again, because I have equal sample sizes. So my my effect size is going to be the difference, 5 divided by my standard deviation is going to give me an effect size of 0.5. If I take 0.5, multiply this by the square root of 25 over 2. Again, not 50, not the whole sample, just one sample, okay? Go through and run that. What's the value I get for my non-centrality parameter here? What is it? 1.77?
Yeah.
Okay. Cool. So again, if I go through, find 1.77 on my power table, go down, look over, I get power of about 0.43. So better than the last one, but still not great, right? Again, so I'm saying, assuming the null hypothesis is false, my effect is expected to reach statistical significance about 43% of the time, given 25 people per group and a population effect of 0.5. So again, these are bad Vegas odds. These are games that you should not play, because you're going to lose more often than you win, okay? This isn't even a coin flip, right? So if you want to go through and test this with my sample of 25 in each group, or a total sample of 50, I've got less than a coin flip's chance of identifying this effect, even though the effect is real, okay? And it's an effect at a medium size, right? Like, it's about a half standard deviation difference. And so this may not be trivial, right? But I'm not going to find it with the sample that I have very often. Same thing, what is the sample per cell? And again, remember, we're talking about per cell to achieve power of 0.8. We take this, do some math, we get 2 times my non-centrality parameter over D, square that, right? Which is, again, is going to translate to, in this example, 2 times 2.80 over 0.5 squared, okay? And again, 2.80, this is like a z-value. It's always going to be the same thing if you're looking at power 0.8, right? Someone give me my sample size that I would need to adequately power this study if my effect size, if my estimate of effect size is accurate here.
63. Yeah.
What is it?
63.
Okay. So what is my total sample size?
126.
126. Okay. And so remember that, because again, this is looking at each sample, right? So again, each cell, I would need to have 63 people in each cell. Total sample, 126, which is considerably larger than what I had here. Okay. So again, we're just making type 2 errors right, left, and center in this scenario. We need to jack up my effects, or my sample size. Questions about your independent sample team? All right. Now, if I don't have a completely balanced design, if I have unequal samples, which is happens most of the time, right? What I need to do is first calculate a harmonic mean n to adjust for those unequal samples. Okay? And so my harmonic n is going to be 2 times the number of people in my first cell times the number of people in my second cell over the number of people in my first cell plus the number of people in my second cell. So if we go back to our stereotype thread example here, right? So my control group has 18 people, has a mean of 9.64. My threat condition has 12 people, I have a mean of 6.58, and my pooled standard deviation for these groups is going to be 3.1. So I go through, calculate my effect size, right? I go through, run this, I'm going to get an effect size of 0.99. It's pretty massive, right? I'm saying there's a full standard deviation between my control group and my stereotype threat group, right? Full standard deviation increase. I don't think, I'm almost certain stereotype threat effects, if they are real, which I think is questionable, are not this large, but in this example, we'll say that they are, okay? And so then what I'm going to do is use the same formula as before. I'm going to take that times n over 2, but this time I'm not using, so one of these, or the average, I'm using the harmonic n here, which I pulled out and determined to be 14.4. So this is 2 times 18 times 12 over 18 plus 12. Drop that in. What do I get for my non-centrality parameter here?
2.6.
What is it?
2.66.
2.66. Okay. And so again, this is going to give me power of about 0.75. Okay. And again, assuming the null hypothesis is false, effect expected to reach statistical significance 75% of the time given samples of 18 and 12 with a population effect of 0.99. So quite a bit better, right? But here we've got a massive effect size here that we're looking at. We've got an effect size of 1 essentially, right? So even with that big of an effect, we're still not quite hitting what we would call identify as adequate power. Okay. So one thing here to notice though is I have 30 people in my sample in total, right? Like 18 people in my control, 12 in my experimental group, right? So I have a total sample of 30. But if I calculate my effective sample based on my harmonic n, if I take 14.4, multiply that by 2, I get 28.8. So what does that tell us about the impact of unbalanced samples on my power? What do you think, Lucas?
That it makes it more difficult to achieve power.
Yeah, it negatively impacts my power to some extent. It's not the end of the world, right? Just like I would for sure wouldn't say like, oh, I've got 30 people in this group and 60 people in this group. I wouldn't get rid of 30 people in the one group to make sure they're balanced. You're going to lose more than you gain there. But in general, think about the impact of having unbalanced samples, right? I'm losing 1.2 people based on just the imbalance across these cells, right? And so as you start to get increasingly unbalanced designs, that's going to start to create a lot more difficulties and things along those lines. So again, something to be aware of statistically when when thinking about this in terms of as we start to deviate from the vacuum in which these sort of statistical models were built, it starts to have impacts on things. All right, questions about the independent sample stuff?
So is the harmonic mean and the same as the pool standard deviation?
No, No, this is just, so this, your pooled standard deviation is your pooled standard deviation. This is just a harmonic, this is just a